All right, let's get started. Yeah, thank you for having me here. And we're running a little bit late, but I'm very happy to share my work here with Cohere Labs Embodied AI group. I'm Chang, currently a fifth year PhD student at UT Austin. And today I'm going to present our work on FLAM scaling latent action world models with factorization. It's a work jointly with all my amazing collaborators. So let's start with some motivation. So why we think this is an interesting area to work on. So there has been a lot of efforts from the embodied AI community to gather more and more data like R1, Droid, uh, Bridge Data, Groot, but people believe that why robotics area hasn't reached the level of success as a large language model is that robotics data are really hard to get. If you want to get expert demonstrations, you either let a trained agent with some trained policy to collect the data, or let a human expert teleoperate a robot. And those data sets are difficult to scale, and it's limited to specific hardware, and also the environments might not be diverse enough. On the other threads, people start to think of using in the wild internet videos. For example, Ego 4D, EGTEA, those ego-centric videos that's large scale. But there are also other problems of this data sets. The lack of action labels, they might be too noisy with exogenous information, and also there can be embodiment misalignment. For example, if you want to use the egocentric videos, the human are doing the manipulation task, but you want to do policy learning over a robot, then there will be embodiment misalignment. And we decided to tackle this problem first, how to learn a world model from action-free videos where the action labels are missing. So some of the related prior work, not a long time ago this year, Genie 3 published, and it has fascinating demos on how the agent can navigate in a game setting and also interact in the world model. But if you take a closer look at the interactions, you will soon realize there are still potential for improving. So they listing their limitation that accurately modeling complex interaction between multiple independent agents is still an ongoing research, which means that currently most of the world models only work in a setting. There is only one agent doing actions, but what if there are multiple agents moving around and interact with each other? And this is actually a pretty common scenario in real life. For example, in a crosswalk uh, autonomous driving case, there will be pedestrians, multiple cars moving around. And if you only model your own dynamics, that sort of won't work. That's the reason we want to narrow down the case where multi-entity scenario, and we want to learn a world model without action label on the multi-entity area. So some preliminaries, what is latent action models? So latent action models is a very popular model that used to a sort of world models that's used to model the dynamics while the action labels are not available. It jointly trained an inverse dynamics model and a forward dynamics model to learn the latent action space. So giving a video, you have a sequence of frames. So you use your current frame and next frame to do inverse dynamics to predict a latent action space. And then you use that latent action and your current frame to then recover or predict the next frame. And if you think of this structure, like it's pretty easily that you can learn like a shortcut, very simplified solution by just copy paste the next frame. Then this won't actually learning anything meaningful. So usually in this models, people would usually add the quantization on actions, which usually in implementation, it becomes learning a small action code book to ensure like the latent action is not just copy pasting the next frame. But here is a very important assumption. So this kind of model only works, I would not work, I mean, relatively works when there is only one moving agent. So the model would compress all action-related information into one single latent action in order for its dynamics prediction. But as we said, for example, the crosswalk case I just mentioned, what do you mean by learning one single monolithic action for the entire scene? That this action is manipulating how all the cars and pedestrians are moving together. So naturally, this does not make sense and leads to our design that we should do factorization over the latent action world model, and which leads to this work FLAM. So basically, we are trying to factorize the state representation so that each factor is attached to one moving agent. So in this case, the dynamics of the blue car, green car, and the pedestrian would be learning independently. And this could lead to more accurate modeling the world.
I had a quick question. So
Yeah.
you mentioned that inverse dynamics model and forward dynamics model. So by inverse dynamics model, like, are you trying to predict the torque, or like what?
Yes. So like in robotics area, inverse dynamics, if the action labels are available, you could be predicting the proprioceptive torque, velocity, and those real physical meaning actions. But since we are dealing with action-free video, so in the model learning stage, the latent action is you can consider it as a latent feature that's compress all the information that's needed for dynamics, but it's not really learning a vector that has physical meaning. Does that make sense?
I see. I see.
Yeah. Yeah. Feel free to interrupt me if you have any questions during my presentation. So the major assumption of our work is that we assume the factorization of the states and learning dynamics model separately for each of the entity would help the world model to be more accurate. In the following presentation, I would sometimes use entity or agent. This terminology, they are pretty, they are equals to each other. So in our design, for simplicity, we make assumption that the dynamics of the entity are independent to each other. And this leads to our design. So a scaling latent action world model with factorization, it comes with a two-stage training pipeline. The first stage, we do feature extraction pre-training, where an quantized version of autoencoder style architecture is used to extract discretized information from the states. And this after this training stage, in second stage, the encoder and decoder and the feature extraction quantizer, FSQ, here are freeze as a feature extractor. And then we start to train our factor latent action model. So given the state feature, we would first use a factorizer to factorize it to K in factor embeddings. And in implementation, we are using slot attention for the factorizer. And then use the embedding for each slots, and also the embedding for the slots from next frame we jointly training the IDM and FDM I just mentioned in few minutes ago. And then after the slot embedding prediction for next frame, we aggregated back to the feature space. And the only learning signal here is the difference between the Z and Z hat on the T+1 frame. The reason I want to emphasize on this is that a lot of people are use slot attention to extract object-centric representation, but we think that might be emphasize the representation too much on the superficial visual features, but not really the ones that are helping the dynamics modeling. So in the second stage, factor latent action model training, we're not using any like current frame reconstruction loss, but only the prediction loss from Z and Z hat on next frame after it passing through the dynamics model. And also, if you haven't find that, though I mentioned that we wanna disentangle everything and learn separate inverse dynamics model and forward dynamics model for each of the entity, we still sort of input the K factors from all the factors from current frame. This is because even though your different entities are acting independently, their dynamics are independent, but while you are acting, you cannot avoid the interaction with other agents. So this modeling this kind of interaction is very important. So we want to include all the information from other factors to help the dynamics learning as well. I will discuss this more in the later slides, that if there are better ways to model the interaction between different entities.
In, I guess one question I have in your previous diagram is, so these Z hat and Z, these are action, right? These are
So these are state representation. So
okay.
yeah, I should have started from the the symbol and terminologies. The O here are the observation space. It's the raw frames from the videos, and Z is the state representation space where we extract features from the frames. And S here is the slots embedding, which after we applied the factorizer on our state representation, it becomes K factor, and each one have its own representation. And A here is the latent action we're learning here. So the only learning signal on Z is on the feature space. Yeah. Does that answer your question?
Yeah, I think Reza has a question. Go ahead, Reza.
Thank you. I was wondering what this is that we are taking Z from the next time step and feeding it into a process on the previous time step. I don't understand this time.
So your confusion is at the
ZT+1. Why
okay.
is that being fed back into the time step together with time step T, and it looks like somehow the future and the present are being mixed?
Yeah, that's a great question. So the inverse dynamics, the definition of it is when you have your current state and next state, you're trying to inversely learn back the actions. So like without a future frame, that feature, it would not be called inverse dynamics, because learning action or latent action purely from your current state is a policy learning structure, not a dynamics learning structure.
I see.
Yeah. So
Oh,
I
okay,
would say
okay,
like
okay.
I would say the input of future frame Z feature is only
I see.
used
Okay,
in the training stage for learning the IDM and FDM.
okay, okay. So,
But
so this is
yeah, but in inference time, because you are living at your current time, you would not have the access to future.
okay, okay. So
You know,
that is
so
kind of your reward signal.
yeah,
Okay.
so the
So,
yeah,
sorry about that. Yeah,
as I
okay.
mentioned, the only learning signal is on that. Yeah,
Could you please very briefly remind us what FDM and IDM are?
IDM is inverse dynamics model, and FDM is forward dynamics model.
Thank you very much. Thank you.
Thank you for a great question. Yeah, and for the inverse dynamics model and forward dynamics model I just discussing, we are using similar spatial temporal transformer architecture, just as Genie is using. So then this leads to our entire algorithm design. So in the first stage, you would initialize and pre-train a VQ-VAE style of feature extractor with a reconstruction loss for your current frame. And in the second stage, you use the trained VQ-VAE and freeze it as a feature extractor. And then you extract, or I would say decompose the factors, or we call it slots, using slot attention. And then for each slot, you infer the latent action and then predict the next frame slots. And then at the end, you map all the slots back to the feature space and use the Z feature space loss as the only learning signal for optimize our factored latent action model. And we test this model on 5 different data sets, including multi-grid, ProcGen. Those 2 are simulation environments, and also real-world data sets like NewPlan, Sports, and eGTEA. NewPlan is autonomous driving data set, and Sports is data sets we put up by ourselves, but including data sets, data on like basketball, tennis, and volleyball, etc. And eGTEA is a egocentric human manipulation data set. The reason why we put we pick this 5 data sets is they all includes multiple entities moving at the same time. And the eGTEA, we would hoping like the bi-menu would be representing 2 agents in our case. So to evaluate our model, there are 3 different ways. First is video reconstruction quality, which is commonly used for video modeling and world modeling people. Another metrics we are using is controllability. This is telling us how much adjustment a user can apply onto video generation through the latent action. So basically, after you learn the factored latent action world model, because as I mentioned before, we add discretization on the action by learning a latent action codebook. This codebook, you can later use let the users select a factor and select which action in the codebook he want to execute. And then by this user specified signal, we can use the model to generate diverse kind of new videos. And also you can use policy quality to evaluate how good your world model is. Basically, you use the world model you learned as the model in model-based RL or other policy learning methods, and the average episodic return of the policy could be a signal of how your world model is help the agent learning. So we end up using, for the VQ-VAE part, we end up using the Impala for the encoder and LAPO for a decoder. And here are some examples of how this feature extractors can reconstruct the frames. And after this feature extractor are learned on the second stage, we use that for the FLAM training, and we compare our FLAM with 3 different baselines. The first one is world models, where we use the ground truth action label as the action input instead of the latent action we learned. The LAM, which is or we can call it LAPO, which is same as the non-factorized version design using LAPO, but we changed the feature extraction part to align with our design. And the OC plus LAM is object-centric representation plus the latent action model, which is using the acceleration reconstruction loss I was mentioning before, which we do not use in FLAM. So we distinguish FLAM from other object-centric world models with the emphasis that in our latent action model training stage, we do not use reconstruction loss for factor representation. And we believe that would benefit the representation to be more dynamics focused than visual property focused. And here are some qualitative examples on the multigrid. So the first row is the ground truth, and the next 3 rows are use the latent action world model. The one with plus the object-centric representation, and the last row is our factored latent action model. You can sort of find latent action model has some errors in the first few frames, and the object-centric representation messed up, and our factor latent action model modeled perfectly on this toy setting. So this actually validates
the colors in the, like, what are those different colors mean? They are different objects, or
so in the multi-grid environment, like each color of agent is independently moving around. At each time step, they have 4 different choice of action. Stay still, go front, turn left, and turn right. So we are trying to do the world modeling by capturing the dynamics and predict, okay, I know where next probably this agent will go.
I see, thanks.
Yeah, so this experiments in the simulation actually validate our assumption that using the representation that's jointly training with dynamics instead of pre-trained object-centric representation would make it rely less on the superficial visual features, but better focusing on the information helps for dynamics modeling. And also, we think the benefits comes from factorization is because factorization is actually disentangle the dynamics of multiple entities. Before the factorization, everything seems to be learned together, but now we make the world model more structured so it can capture the dynamics more accurately.
I guess one question I have on the factorization is, so it looks like it's working well in sort of like the visual scenarios, like where you can see the different pieces like moving and kind of like disentangling. But like I'm curious because like there are other types of data, let's say time series data, or like let's say data about human behavior, let's say, right? Where human behaves independently of each other. Sometimes there is relation, but a lot of time there is not. So I'm curious, like if this technique can be, the factorization technique can be applicable in those scenarios.
Yeah, for sure. This is definitely the area we're interested in because we start this project because we want to use real world data to maybe help modeling scenario where humans would interact with each other or robot interact with each other. I will go into our experiments on real world data soon. Yeah.
Sure, thank you. And there is another question from Kevin. Go ahead.
Hi. One observation I made is that if you go back to the grid the grid one, in this dynamics model, is the k equals to 4 because there are 4 moving objects?
Yes, you catch that exactly. We deliberately set it to 4, so it's better for visualization. But in other cases where the number of agents is not known in the scenario, you can set k to a relatively large number. So the factorization capacity is enough, but then you can later do prune on it. Yeah.
That makes sense. So what I was going to ask is, yeah, so you mentioned followed it perfectly with the idea that like in real world scenarios, the number of independent entities is unknown. So let's say that you have a very large and the number of entities are actually very, very small, then what would actually happen to the inverse dynamics models of the big K minus small k that aren't actually representing an independent model? Would they just repeat the learning of a dynamics that is there? So for example, in this example, if you had k is equals to 12, would there be um, three factors that would be learning the same um, like independent agent? Or would it be that four factors would learn these agents and then 8 factors would learn nothing?
So the factorization is on the feature space, but I can show you some of the attention masks that's showing which factor is attend to which area. I would say like if the number of k is uh, like in a larger amount larger than the number of entity, then it will be end up doing more factorization in the noisy background, which in the reconstruction aggregator, it can be ignored by our aggregator. And also in the policy learning, you can use an attention methods to filter out those like more like information that you don't want. Does that answer your question?
Yes, thank you.
Yeah. So while doing experiments, we have a lot of different detailed designs coming up from our mind, and we realize, oh, there are so many different things we need to think about after we did the factorization. The first thing is entity tracking needed? So as I said, that using slot detention for state factorization would make the state factorize into different factors. But because we want to learn independent dynamics model for each of them, then you sort of need to make sure the slots ordering in your current frame and future frames align. Otherwise, if, for example, here, the order of your slots in your current frame is yellow, green, blue, and the next frame, the slots order are blue, yellow, and green, then you are learning fake dynamics that mapping an entity A's states to an entity B's future states. This would mess up our structured latent action model. So the problem is that slot attention we use start with random initialization. It won't actually ensure this kind of same order for the sake of our learning. So we try different ways to force this consistency. So we tried Hungarian matching to first sort them in the order of embedding similarity and then do hard matching. And we also tried soft matching like influency constructive loss uh, and sinkhorn matching. And it turns out those methods did not work well, but we end up with a solution that we initialize the slots of current frame with the slots from last frame. So basically, you have an initial guess of factorization from a historical frames, and we start a little bit fine tuning on your current frame, so that the slots would align with each other. So if you see from the visualization here, the upper image is showing without the recursive slot initialization. It seems the attention mask is focusing on a bigger scope of area, but after using the recursive slot initialization, because the slots are now aligned, the dynamics help the slot embedding to be more dynamics aware, and each of the color in the slot attention represents a factor, and it starts to narrow down and really focus on that one single moving agent. But there is also like there are pros and cons. The disadvantage of this method is that it would be slowing down our training a little bit. So we're still actively thinking of a better way to improve this. Now it comes to where like the previous question, like how this model perform on real world scene. So we tested on new plans, sports, and EGTA. As you can see from the PSNR, which is the reconstruction loss, it sort of did not surpass latent action model without factorization, which is out of our expectation, but the controllability is still pretty good. So when we were analyzing why this happens, and it comes to several potential reasons. The first is, as I mentioned before, perfect factor tracking is a necessity for the for our model to work, and also if the video used for modeling is longer, you also need to consider a re-ID problem. If an object disappear in several frames and show in the later frames, how are should they be attended by which factor? So this questions hasn't been investigated a lot. So we think this is an area that can be helping the factor latent action model to work better on the real world scene. And also there is a problem that unlike the simulation environments where the agent action frequency are pretty aligned, like several seconds, the agent might move or the robot might move at a certain frequency, but in the real world videos, the action speed of the different agents are pretty volatile. So it makes it harder to model it with a fixed frame sampling rate. So here are some qualitative examples on the sports data set we put up together, like from the eye viewing factor latent action model, like did not perform super better than the latent action model, and all the three baselines has a little bit reconstruction error when it coming to the rollout. So here are some lessons we learned from our experiments. The information.
Is it okay if I ask a question?
Yeah, sure. Please interrupt me anytime.
Thank you very much. I'm not sure how you. So you said that you keep the slots from one time frame to the next in sync, right?
Mm-hmm.
Basically, you initialize the slot orders in one frame according to what they were in the previous frame. I'm wondering that does it not at some point have to switch?
Well, why
Um,
would they need to switch? Because the ideal case is that we hope one factor always focus on the dynamics of one agent. So the perfect learning results would be the slots are always constant.
um, right.
So when I mentioned the initialization, it's initializing the
I'm,
embedding of
I'm
the, yeah, it's not the attention mask or like how the slot attention is calculated.
okay. I must have missed something very important. I'm thinking of the model that produces the different that produces the entire state, and then presumably from that you're extracting the different slots, right?
Uh-huh.
You're splitting it into different slots, and I'm wondering, for example, if cars on the road change places or whatever, this one single model that is producing all the different slots, is it not going to put the, the the part of the state that belongs to that car, if the car goes to the right, if they switch places, does the model not produce a different order? So I'm sorry,
Oh,
this question.
now I get you what makes you confused. So while I am saying the order of our slots, it's the index order in our model. It's not the XY or physical location in the scene. So we
Right,
want to, yeah, we want to keep the
right.
index to be consistent so that one factor is constantly attend to the dynamics of one agent. But in the meanwhile, the agents are moving, so the exact numerical value of the slot embedding is changing, and the location of the agent is changing. As you can see from the attention mask here, the mask is changing. So which means each factor, the attending area of it is actually changing following the agent. So in your case, when the car is turning a right and the physical location, it changes, but we hope the slot embedding would capture that change of location. Does that make sense?
Right. So when the model changes the locations, how does that get tracked? So when the model that is producing the different slots produces a different order for the cars.
Oh, so you're asking,
You,
yeah,
you,
that's exactly this slide is talking about. We actually need the entity tracking. So this is we do the initial the recursive initialization is based on a computer vision assumption that the motion is continuous. So your current frame and next frame, your car cannot like suddenly from your view and disappear, or like make a sharp turning just one frame and it just disappear. It's not possible. So in the real world scenario, potentially in your current frame, if your car is in the car you're looking at is in the center of the frame, and next frame it will be slightly moved to the right. And so we initialize the slot attention embedding from your current frame to next frame to give like a starting point for the initial guess of the slot attention, and then iteratively do several iteration of fine tuning of the slot attention to make the adjustment for that turn right motion for the car. Does that make sense?
Sure. So it moves continuously, but is there not one point where the slots switch order, where the model produces, where the model produces an embedding with 3 different slots, and the slot for the green car has suddenly shifted from slot number 1 to slot number 2? Does that not happen?
I mean, that happens. That you catch the point. That's why, like, we're saying we have pretty good results in the multi-grid environment where all the agents are always in your scene scope. But in the autonomous driving, you can see it seems like the FLAM did not surpass the non-factored version of latent action model that much. So we think it might. I mean, the object disappears thing you mentioned, I think that could be a possible reason. Yeah.
But I'm just wondering, how do you deal with that when the orders switch? Because you said that you try to match them from one frame to the next. So if the orders switch, how do you track? How do you know that the model has switched the order of the slots?
So it comes to my answer to the previous question. We would, so if this car disappeared in the next frame, so the number of agents would be changing. And that's why we would have a larger K, hoping that by large amount of slots, each one would attend to one agent. But like if the next frame the agent disappeared, then the embedding it learned is not improving, like not learning any numerical meaningful number, and then in the aggregator, it can be annoyed by our aggregation, or you can design your own prune function to filter out those noisy data.
I think for the sake of time, we can take it offline and probably move on.
I would be happy to know, like, if you have any insights on this.
I think I have understood what you're saying. You're saying that you're making the assumption that most of the time the transitions are continuous.
Yes.
If I'm not mistaken.
And
I apologize about the misunderstanding. Okay, thank you.
Yeah, and I understand you are talking about all those corner cases, and I would say that's also a limitation a lot of the world modeling work needs to improve on. I agree with your insights. Yeah, so let's come back to some of our findings on our factored latent action model. So we find, as we mentioned in the preliminary, that the classic way of using latent action model, people would apply a latent quantization as an information bottleneck to avoid the model from collapse. But is it indeed beneficial or adversely limiting the model capacity? And our finding is that yes, when there is no state quantization in the latent action model, the action quantization is the only way to ensure the model is not copy-paste next frame. But when there are state quantization, and especially in our case, we already have the factorization as an information bottleneck, there is already enough of discretization here. So action quantization actually hurts the model capacity. So we think this is also something the world model researchers could be thinking more on, about how to choose a good information bottleneck is very important. For example, the causal tokenizer in Dreamer v4, which just released recently. They use a masked autoencoder as information bottleneck for the state representation extraction. This is also an example of how they designed the discretization to avoid the model collapse. And after we learn the factor latent action model, what can it be used for? One potential application is controllable video generation. So after we learned the dynamics model and also together with latent action codebook, then given your current frame, it is possible to manipulate the agent one by one independently, compared to other non-factored world model where you can only manipulate the entire scene together. So here is an example in multigrid where we let the user specify which factor he wanna manipulate, and also which action from the discretized action codebook he or she wants to execute. And it turns out to be on the right, all those are the potential next frame generated by our model. So if the user decides to manipulate slot 1 and randomly choose action from the codebook where we set to the codebook size to 4 here, it would be very accurately manipulating the green agents stay still, go front, turn left, and turn right. And if he selects the other slots, it can also manipulate other agents. So we think this leads to a potential that when human wants to generate the video towards the direction they want, they can manipulate in a multi-entity scenario, agent by agent, instead of saying, I want the crosswalk to be more empty than all the agents are moving entangled together. And this is why the more controllability of our model comes from. So it while it introduced more diversity in the video generation, it also comes with the expense of inconsistency and fidelity in video generation. So we test this user-specified video generation on the autonomous driving dataset. And if you take a closer look here, you can see that it seems in some of the generated frames, the leftmost white car suddenly disappeared in the image, upper image. So this is a disadvantage, and we sort of need to treat this limitation seriously. And a different application for our model is for policy learning on action-free video, and it would become a 4-stage pipeline. So basically, the latent action we learned from our model, its dimension does not necessarily align with the real action dimension, because the real action labels at the learning stage of our model is not available. So we need to learn a latent action decoder from the latent action dimension to the real action dimension. So the 4th stage would be latent action model learning, then use that model to label data, and then learn the decoder, and all together to train a policy. And what we think, like where we think this is useful is that the latent action model can use the large amount of action-free data to model a very accurate world model. And then in the latent action to real action decoder learning stage, it only needs a few samples of real action rollouts. So it would lead to a few-shot learning, which both taking the advantage of large-scale internet data and also a less labor on collecting real rollouts for training. And for the decoder, can be different design choice, like learning a mapping to select which actor is the closest to the real action, or cross attention. But the reason why I mentioned this is because in the factorial world model, after you factorize the agents, you actually do not know which agent you can control. It is pretty natural for a human to look at the autonomous driving video and know the car that's close to my angle is the one I'm controlling. But for model, it does not know which factor it's possible to control. So this what leads to a limitation of this kind of model. We have to specifically design a different methods to decide which factor is controllable by the agent. So currently we do it implicitly, but is there an explicit way to learn this? And also the state embedding of a single factor still still contains several exogenous information. And also, if you still remember, we made the basic assumption at the beginning that each entity is independent of each other. But this is not the case in real world scenario. Usually the forward dynamics are independent, but the actions are not independent. In the autonomous driving or social navigation setting, the action you take, which direction you want to go, largely dependent on the motion of other pedestrians, because you want to do collision avoidance, etc. And the other limitation I mentioned is that the IDM here we are using is using a spatial temporal transformer, but considering there might be multi-model distribution there, diffusion or flow matching architecture could be helping a more accurate modeling of the world models. So we leave those for future works. The first is unrealistic video generation. Maybe by injecting more physically grounded priors can help make the video generation more realistic and also physically consistent. And also world modeling and policy learning are currently a separate stage training in our model, but they can actually be joint. So in many VLA works, people would fine-tune the world model with a small portion of real action conditions to help further improve the accuracy of a world model. And most importantly, we definitely want to scale up with more data and also maybe do planning over it. So the area we find this FLAM model can be useful is either use it as a pre-training stage in vision language action model, and also it can help in the cross-embodiment learning. So if we can learn a world model on the egocentric human demonstration data, and then use the model directly, do policy transfer onto a robot data, then that would be fascinating because we do not really need to teleoperate the robot to collect data. Yeah, that's basically our work. Thank you for my collaborators, and a little bit advertisement here. So I am a PhD student at UT Austin. I am co-organizing a UT reinforcement learning reading group there. And if you are interested in joining the discussion or research collaboration, or just making more friends, feel free to reach out. Yeah. Any questions?
Is there is there a link for, maybe I can search and find out.
Yeah, I can send in the Discord later. I have the link. So I can handle that.
Yeah, thank you, Cole.
Yeah, totally. Cool. Yeah. If there's no other question, actually, we're at time here. So, Chang, thank you so much for coming and
We're
presenting.
sharp on time.
Yeah, I know you've got to run here too. So, thank you so much for your time, and really, really appreciate the presentation. Really cool work, and really cool downstream applications here too. So, yeah, thank you for your time. You're the best.
Thank you everyone for coming.
Thanks.
All right.
Bye.
Thanks everyone.